Okay guys, in this last video we're going to be taking a look at the definitions of what we call linear speed and angular speed. So let's go ahead and start by reading through this first sentence here to kind of set up the context here. We say if a point is in motion on a circle and the circle has a radius r and it moves through a central angle of theta radians in time t, then its linear speed is defined as v equals s over t, where we're going to indicate something here. We say S is the arc length given by S equals r theta. So I want to go ahead and set this up here, and I think that this would be a good picture to draw. What we're saying is that given a point on the outside of the circle, and I usually just use the point P here, what we're doing is we're saying that there's kind of this imaginary line, this radius line that connects this point to the center of the circle, but let's put it in motion. Okay? And what I mean by in motion is it's not in like varying motion. What if we put it in what we call uniform motion? That is to say that it's always going to spin the same speed, same speed, same speed, same speed. The thing here is we often want to calculate its speed. And so there are two different ways in which we do tend to calculate its speed. The first one being its linear speed or its line speed, or how much it changes its distance over time. Okay, so when we talk about linear speed, this is a distance over time relationship here. Distance over time. This is the same way we measure your speed when you drive down the road in kilometers per hour, or say miles per hour. So distance over time, where S is given as our arc length. So to look at what we're saying here is we're trying to ascertain or determine how far did you travel around the outside of the circle in any given time. So let's say in a given frame of time, we could say that the point ends over here. We could see that I would have known how far we rotated in terms of theta here. I certainly would want to know the radius length here, and we have our S that is right here over a time frame. So when we defined our linear speed, or how far you went in a line, it's a curved line, we would say that really it's just how much arc length you went over time. And just recall that arc length is really the radius times the angle in radian measurements, okay? So when we say linear speed, we say arc length over time. Okay, this is what I want to write. Arc over time. What I want to make sure we write then is that the velocity here, the linear velocity, is given really as r theta over time. So in any of these situations in which we're finding linear speed, the things that we're going to need to know are what is the radius, what's the angle that it rotated through, and how long did it take it to do this. Okay. So the first way to measure speed is to travel a distance over time. Now, when it comes to uniform motion of a point around the outside of a circle, the interesting thing is we could also define it as having an angular speed. So if linear speed is a change in your line distance over time, then your angular speed, and we're going to define it using this lowercase Greek letter here. This is the Greek letter omega. But we say the angular speed is how much angle you rotated through in a given amount of time. If you were to tell me that there was a point on the outside of a circle and it rotated 4 revolutions every minute, that would give me an indication as to how fast this point is going, because I know how many times it rotated in a given frame of time. So when we define angular speed, since it's angle over time, you're going to see this is a little bit easier. We say that it's just theta over time, or how much angle you rotated through over time. So one thing I'm going to recommend is this. When we talk about this angle right here, we say that the angle is given in radians, okay? Given in radians. And that's true for our linear speed up there as well. We want to give it in radians measurement. But looking at these kind of problems, which we'll take a look at a couple of them here, we're going to determine both our linear speed and our angular speed. So let's take a look at this first situation down here. It says that the hard drive in a computer rotates at 3,600 revolutions per minute. Now the very first thing I want you to do is highlight this phrase right here, because you're going to see it often, and we're just going to use the word RPM. So it goes 3,600 RPMs, which stands for just revolutions per minute. It says this angular speed expressed in revolutions per minute can also be expressed in revolutions per second, radians per minute, radians per second. Using 2 pi radians equals 1 revolution, we express the angular speed of a hard drive in radians per minute as follows. Well, what I want to see here is this. What I know about its speed is that it's 3,600 revolutions, okay, in a given minute. And we do want to write this as a fraction. And looking at this, I would say, well, this is our angular speed, which is given right here. So we said angular speed. So our angular speed is this omega. You notice that what we should have is an angle over time. So because it's given to us in revolutions, one thing we always want to keep in mind is this. One revolution, right? One full rotation around a circle, that's how much in angle? Well, in terms of degrees, it'd be 360 degrees, but in terms of radians, we say it's 2 pi radians. So in order to convert this from revolutions per minute, okay, and changing it into radians per minute, what we're going to say here is that we have to multiply by a conversion factor, which is this conversion factor right here. So we would say that I'll put my one revolution down here, because that revolution here will cancel out with this revolution up here, and I'll say, well, one revolution is really 2 pi radians. And so converting this, essentially, we've already done that. We would say that we already end up in radians per minute, and what we get is 2 pi times 3600 over 1 minute times 1. So we say 2 pi times 3600 is 7200 pi, and we had this top unit in radians, okay, in radians, and our bottom unit here is just 1 minute. So one thing that I would recommend you do is this. We could say 7200 pi, and I'll put over 1, even though I wouldn't normally do that, but we usually have a denominator that's not just 1. And off on the side here we say radians per minute. We put the units off on the side. So we say here's our number of radians per minute, and this would be our angular velocity, and all we had to do was determine how much angle we went over time. So one thing to keep in mind is this. In terms of turning revolutions per minute, or RPMs, into radians per minute, and we're going to make a note here on this one. To calculate angular velocity when given RPMs, we just take the number of RPMs and multiply by 2 pi. Okay. The reason being because if I want to know how many radians you went in a minute, and I know how many revolutions you went in a minute, I know that each revolution has 2 pi radians in it. So we could just say take the number of revolutions and multiply it by 2 pi, because that's how much radian measurement you would have gone through. Okay. So we're going to take a look at just one more example here, and this is just confronting linear speed in terms of angular speed. So on our previous page there, we said our linear speed, that was arc length over time, or distance over time. We said that that's the same thing as theta r over time, since s and r theta are the same thing. Okay. So what we can do is we can actually express our linear velocity in terms of our angular velocity just by doing this. What I'm going to do is I'm going to grab the r and I'm going to put it off on the side so that we really have theta over t, and this is the same theta and t that I have here. And I'm just going to put the r off on the side. And this is still the same thing as what we started with. If I put r over 1 and multiply straight across, I get back my theta r over time. But what I want you to see is that I get theta over time times r, and by definition of angular velocity, we know that theta over time, or angle over time, is really our angular velocity. So what this leads us to is that as long as we know the angular velocity, we can always multiply that by the radius, and that totally gives you the linear velocity. And so that's something that I want to do here. But let's go ahead and first read through this definition here. We say that the linear speed, v, its velocity, in terms of distance over time, of a point, a distance r away from the center of a rotation is given by the linear velocity is equal to the radius times the angular velocity, where omega is the angular speed in radians per unit of time. So you'll notice here that we do need to be in radians still. So let's go ahead and do this. Let's read through this and talk about how we could use what we know from this problem to determine what our linear speed would be. So it says, long before iPods that hold thousands of songs and play them with superb audio quality, it says individual songs were delivered on 75 RPM and 45 RPM circular records. It says a 45 RPM record has an angular speed of 45 revolutions per minute. So we have our angular speed in RPM. It says find the linear speed in inches per minute. Okay, so we want to convert this to inches per minute at the point where the needle is 1.5 inches away from the record's center. Okay, so let's go ahead and start with this. If we wanted to find our linear velocity, I almost wrote a W there. We know that it's omega, it's our curvy W. I'm going to need to know two things. I'm going to need to know the radius, and I'm going to need to know the angular velocity here. So starting with the radius, well, it does say that at a point where the needle is 1.5 inches from the record center, if this is our record that is turning here, then the needle, you know, comes in and hits it kind of right here. Here's my needle. But that radius length right there is 1.5 inches. So our radius is 1.5 inches. Now we just need our angular speed. Now, our angular speed was given to us in revolutions per minute. So we know that it's 45 RPMs, or revolutions. I'm going to write that here. Oops, let me get my pen tool back out. 45 revolutions per 1 minute. But remember, we could take this and multiply it by 1 revolution is 2 pi radians. So again, we could just take our number of revolutions times 2 pi and we'd have our radians per minute. So our revolutions cancel out here. We get 45 times 2 pi is 90 pi. This is radians per minute. Okay, so here's our angular speed. Here's our inches right here, our radius length. We then could say that our linear speed would be my radius length, 1.5 inches times 90 pi radians per 1 minute. Oh, that doesn't look like an M. That looks better. So we don't have anything canceling out here. We can go ahead and multiply straight across, and I'm going to go ahead just so that we don't make a mistake here. I think it's 135, but 90 times 1.5. 1.5 90s is 135, so we have 135 pi, okay, all over 1, and we have this, since radians are really unitless, we only write them to be formal, we really have inches per minute here. So we say inches per minute. And you know, this is an exact value. I think with problems like this, it's often very appropriate also to give the speed in as a decimal. So if we said 135 times pi divided by 1, we would get 424.1-ish, 424.11 inches per minute. Okay, and we could run all over with this one right here. But essentially, here's our linear velocity. Cheers.